Okay, wanted to do a quick video on sampling distributions for means. Still chapter 18. We talked about sampling distributions for proportions. Now we're going to talk about for means. This was an activity I did in my class. Actually, it's carpet. I was still teaching in California. And what we did is we took pennies and students brought them in, random samples of pennies, and we calculated how old the pennies were. And then they created a histogram with the pennies to show how old they are. So you could see that the most of the pennies were 1 year old. And, so most of the pennies were between 0 and 3. And then look, there's one little lone penny over there that was 43 years old. So definitely if you described this distribution of the pennies, you would look at this and say, well, wow, that's really skewed to the right. So definitely not anything close to a normal model, right? So I took all the ages and put them into a program called Minitab and calculated some information. So if we were in class, I'd stop and have you guys tell me all. I've already mentioned that it is skewed to the right. And so if you had to pick your center, you might pick it around 10 or 11 because there's more over there in the 0 to 10 than there is in the 10 to 40. And the spread, though, goes from 0 to 40, and we can talk about the standard deviation. I'm going to have the numbers that I'm going to show you right here. So the mean of this distribution of the ages of the pennies was 11.663, and the standard deviation was 9.816. And I'm kind of considering the pennies that I had that year as so notice that I'm not saying mu sub x bar, which we're going to start using. I'm treating all the pennies that we had in this picture here, I'm treating that like the population, but clearly it's not the population. So there's, a little bit of downside to this activity, that it's not truly reflective because those pennies were really a sample, a very large sample. So then what we did next was we took 5 pennies at a time. So I had students take, and then they only did this from, like, they had 50 pennies, I think. And so they would go through and they would randomly choose 5 of their pennies and calculate the average age of their 5 pennies. So then that would be a sample mean, where n is 5. We use nickels. Get it? Clever, huh? So you can see that when we did this and created a distribution, some of them didn't put the nickels in the right places, but this was supposed to be in between 0 and 2. So any average that was between 0 and 2 for their 5 pennies went here. And then there was one up here between 22 and 24 for their average with 5 pennies. But notice the center shape and spread. The center still looks like it's around the same, but the shape, all of a sudden, it has lost a lot of its skewness, even when n was just 5. So for the center shape and spread, we see it looks a lot more symmetrical than it did before. Still kind of spread out from 2 to 22. So if you calculate the mean, and notice my symbol, I'm calling this now mu sub x bar, because this is a sample size of size 5. And notice the mean didn't change very much from what I had for the population. The standard deviation is much smaller. It's about 4.6. So we have a lot smaller standard deviation. By the way, to approximate that standard deviation, if you go from the center to the edge and then divide that by 3, I mean, this is not exactly normal, so it's not going to work exactly, but you kind of can get an approximation. So then we did the same thing with dime. Well, a sample of size 10. So they went back to their pennies, they shook them all up, and then they had chose penny, and they had samples of size 10 pennies, and they calculated the average age. And then we created a histogram for that. So you can see again that definitely it has lost some of the skewness the original penny distribution had. So then plugging those numbers into my computer software and then looking at center shape and spread, definitely I've already commented on the shape. So for the mean of mu sub x bar, remember this is a distribution of the sample mean with n equal to 10. The mean is still about the same, but the standard deviation is getting smaller. So as the sample size is increasing, the mean doesn't really change much, but the sample size or the standard deviation does, just like we saw for proportions, where we saw a similar change in that if you look back at my Walking Dead PowerPoint notes. So then we took a sample of size 25. And now here it kind of broke down a little bit because because our penny population, we weren't really drawing samples from the actual population, but each student was doing it from their mini population of pennies. So it kind of broke down a little bit. Didn't have a lot, but if I ran it through my software, you can still definitely see that we have a not necessarily normal because we got this peak right there in the middle, but you can definitely see that the standard deviation appears to be smaller. So we have a smaller spread, and the mean is still about the same. And again, the spread is smaller. So then if we compare them all together, so here's the original penny distribution with the n equal 5, n equal 10, n equal 25, and they're all on the same scale to make it easy to compare. And you can see the biggest difference, even though the change in center didn't really change, but what does change is the spread. So the spread, as you increase the sample size, the standard deviation will get smaller, and we actually have a formula, just like we did for proportions, to tell us how much smaller it gets. So if you take the standard deviation from the population distribution, it was 9.816. If you were to divide by the square root of n for 5, 10, and 25, and I don't think I have this all done on the PowerPoint, so if we were in class, I would have done that, and I don't have my system set up to write on this. So you can pause this and do this and compare it, but if you do, you won't find them exactly, but you will find that it's close to what the standard deviations were for the sampling distributions. So it leads us kind of to the formula. Oops, so let's see if I can fix this. Okay, that looks better. So the sampling distribution of X bar, yeah, that's where I was, is the distribution of the values of X bar in all possible samples of the same size from the population. And the penny model I did is not the complete sampling distribution. You would have to take all the possible samples of size 5 from all the pennies in circulation, and we didn't do that. So we only had kind of like a little partial sampling distribution of X bar. So keep that in mind. That's why the numbers didn't work out so perfect. Suppose that X bar is the mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. Then the mean of the sampling distribution of X bar is mu. So we would have mu sub X bar equals mu, and its standard deviation is sigma over the square root of n. So you've got a couple of formulas then, and if you look on your yellow sheet, you'll see those listed for the mean as well. So X bar is called an unbiased estimator of mu. If you remember, I did the little, in the proportion one, I did the little arrows, shooting the arrows into the target. So X bar is an unbiased. To reduce the standard deviation by a half, you have to take a sample 4 times larger, because this is the formula for the standard deviation of your sampling distribution of X bar. You take the standard deviation of the whole population and divide by the square root of n, so whatever your sample size. So for example, if you took something a sample 4 times larger, the square root of 4 is 2, so you would chop your standard deviation in half. That's something good to remember. We do have some conditions for this, and we'll talk more about this when we have class next week. The population needs to be at least 10 times as large as the sample, so we have had that issue before, so we know that. If the population has a normal distribution, if it's exactly normal, and we know it's normal with a mean and a standard deviation, then the sample mean is also going to be exactly normally distributed, with a mean mu and standard deviation sigma over the square root of n. So that means we don't have to say approximately if we're told that the population that it comes from is normal. But if the population is not normal, like the pennies, clearly not normal, it was very skewed to the right, and if n is large, then so n has to be large, and we're going to talk about how large. We kind of use an idea as about 40, if it's 40 or larger. But remember, not too large, because it can't exceed 10% of the population. So we still have those conditions. It has to be large enough, but not too large. Then the sampling distribution of the sample mean X bar, we would have to say is approximately normal, with mean mu and standard deviation sigma over the square root of n. So sometimes you have to say approximately normal, and that's if the population was not normal, like the pennies. But if you're told that your sample comes from a normal model, then you would not use approximately, it is just normal. The law of large numbers says that as the number of observations increases, the mean of the x bar values gets closer and closer to mu. So as you increase the number of observations, then your x bar values, which is not saying increase your sample size, it's increasing the number of x bar values you have. Then the mean of those x bar values will get closer to the true mean. So this is different than, like I said, than increasing the number in the sample. This is saying increase the number of samples, then you get closer and closer to the true mean. So that just kind of gives you a little idea, a little overview. You've got your textbook hopefully, so you can finish reading chapter 18 and then finish your chapter 18 reading guide.